make sure everything is working. I mean, it should work if you know how to type, because everything was in the book, right? But we're going to talk about everything, but I went ahead and modified this slide so that I could talk about this concept here, because this is very important, a very important concept to understand when it comes to OSPF as well. It's tested on, it's in the book, slide 58, but the diagram is completely different, so I don't know how much it will help looking at the diagram in the book. But so there is a process in OSPF called the DR-BDR election process. It stands for Designated Router, Backup Designated Router. And here's how it essentially works. First of all, this election process only occurs on multi-access networks. This is a multi-access network, okay? So imagine there's a switch, a bunch of routers connected to that switch. Normally what would happen, if this was EIGRP, how many adjacencies would router 1 have? If this was EIGRP, how many adjacencies would router 1 have? Router 1 is the one with the router ID 1.1.1.1. 4. It would have 4, right? It would have an adjacency here, an adjacency here, here, and here, right? And how many would router 2 have? There, there, there. And router 3, there, there. Router 4, there. You get the idea. Right? Lots and lots of adjacencies. With EIGRP, it's not as much of a big deal, because in EIGRP, we're not exchanging a whole bunch of detailed database information. But in OSPF, we're exchanging a whole bunch of detailed database information. So what they decided to do is they decided to have an election process to elect a chief for that link. That's called the DR, or the designated router. Here's how the election works. It's the router that has the highest priority on that network. Now the default priority is 1. So if you don't change any of the priorities, I have here, but if you don't change any of the priorities, these are the priority values. If I don't change any of the priorities, then the tiebreaker is the router ID. All right. The highest priority wins, the tiebreaker is the router ID. So let's assume that all these routers get booted up at the same time. Who's going to become the DR?
5.
Router 5? Which one takes precedence, router ID or priority? The DR is the highest priority. Router 5 has a priority of 1. Router 2 has a priority of 10.
Highest, I'm sorry.
10 is higher than 1, right? So router 2 becomes the DR. Simple enough, right? Even though router 2's router ID is lower, it becomes the DR because the priority on the interface is higher than every other router. So what does that mean for the topology? Well, here's how it works. Router 1 forms an adjacency with router 2, router 4, router 5, and router 3, and that's it. 5 and 3 do not form an adjacency with each other. So if something changes on 5, it notifies the DR, and then the DR then notifies everybody else. The idea of this whole process is to reduce the amount of overhead on that network. So the DR is kind of like a middleman. It's the chief. It's the one that kind of brings all the information together and disseminates the information back out. Okay, simple enough. Who's the BDR? The BDR is the next router in line, right? Router 4. It has the second highest priority. And if the DR fails, this guy becomes the BDR. So far, so good. You guys follow what I'm saying? Yes? No? All right. Here's the problem with this process, and this is why Yasmina had a question about, should I change the router ID to ensure that a particular router becomes the DR? Here's the problem with this process and why it's so difficult to manage in a network. It is a non-preemptive process. Does anybody have any idea what it means to say non-preemptive? What does the word preempt mean?
Sorry, for him.
To sign for somebody?
No, decide beforehand.
Oh, to decide for somebody? Yeah. A preempt means to override, right? Preempt means to take over. In a preemptive election process, if there's a particular protocol for an election, if somebody comes online that meets that protocol, they take over that role. In OSPF, whoever gets elected as the DR stays the DR no matter what happens on the network. So if you happen to configure router 1 first and router 1 comes up first, it becomes the DR, period. Even if router 2 comes up later, it doesn't matter because router 1 is the DR. Router 2 cannot preempt router 1. You follow what I'm saying? Once you become a DR, you stay in that role until you fail. So what I was telling Yasmina is I said, in today's modern networks, the reason why you would want to influence who becomes the DR is because of processing power. You don't want the DR to be some crappy router that can't handle all of the advertisements and the adjacencies. Most of our routers today can handle those adjacencies just fine. You follow me? So we don't really care who becomes the DR. Because in order to ensure that a particular router becomes a DR, you pretty much have to zero out all these other routers. Because if you have a priority of 0, you can't become the DR. To ensure that this router becomes the DR. The problem with that is if all these other guys are zeroed out and router 2 fails, then I don't have a BDR, which means I can't form adjacencies, which means OSPF stops working. So even though there are rules for the DR-BDR election, those rules are only followed if the routers are built in a specific way. That's it. So in a nutshell, there's really no control over it. We're going to have a DR-BDR election on this link. We do not have a DR-BDR election on that link. How come there are no DR-BDR elections on that link? What is the purpose of doing a DR-BDR election? To reduce the number of adjacencies that you have to have. I can't reduce the number of adjacencies on a point-to-point serial link. That's not possible. So by default, the priority is 0 on these links, and there's no DR-BDR election that takes place on these interfaces. Is there going to be a DR-BDR election down here? Straight line means what type of connection? Ethernet. Is there going to be a DR-BDR election down here? Yes. Even though there's only 2 routers, we still have Ethernet. Ethernet is multi-access. Who's going to become the DR-BDR for that connection? Assuming that the routers boot up at exactly the same time, which is never the case, router 7, right? Router 7 has a higher router ID. So on the test, they're going to ask you who becomes a DR BDR. You have to make the assumption that all the routers boot up at the same time. This guy becomes a DR, this guy becomes a BDR, which is kind of silly because they're backing each other up, but that's the way it works. This guy becomes a DR, this guy becomes a BDR. If you're not a DR and you're not a BDR, you're a DR other. We'll see that as we do our investigation, but hopefully that kind of answers Yasmina's question, and hopefully that kind of answers your questions on what the heck a DR and BDR is. We're going to see this as we go through our topology. You'll see how this actually changes when we're looking at our topology. So let's go back to, never on point-to-point links. There is an exception to that. As with anything, there's always an exception. In frame relay, you can configure point-to-point links as multi-access networks. So you could potentially see a DR-BDR election on a point-to-point serial link with frame relay. But by default, that shouldn't happen. So here is part of your network. In fact, this is the, well, not the only part, but this is a part where we have 3 routers. Everybody agree that this is a multi-access network. Following the logic that I just described, who becomes the DR on this network? Anybody?
3's hiding over.
Sorry?
3's hiding over.
3?
He's hiding on the 3. He's hiding.
Well, these are IP addresses. These are not priorities.
Right. But the ID.
But the router ID, yes.
Yeah.
This guy becomes the DR because it has the highest router ID. That's assuming that all the routers are booted up at exactly the right time, same time. This guy becomes the DR. This guy becomes the BDR. If the DR fails, this guy gets promoted, and then this guy gets promoted. What happens when this router comes back online? Nothing. Once you're elected, unless you fail, you stay in that position. So even if the DR gets elected correctly, if it happens to go down, even for a few seconds and come back, it's no longer the DR. This is a non-preemptive process, which is what makes it so difficult to control. All right? So let's see if you guys go into router 3, run that command. Let's see who your DR and BDR is. Go into router 3, run that command. In this particular case, let's talk about this table because it's different than EIGRP. The neighbor ID, in EIGRP, that was actually a physical IP address. What is it in OSPF? Is that an actual IP? No. It is a router ID. The router ID shows up everywhere in OSPF. So the neighbor ID is actually the neighbor's router ID. Full state means full adjacency. Router 2 is the BDR in our case. Router 1 is a druther, which means that router 3 must be the DR. Now yours might look different. It just depends on which router you configured first. If you configured router 1 first, then router 1's the DR. If you configured router 2 first, then router 2's the DR. That's kind of the point I'm trying to make, is depending on which router you configured first is the one that's going to become the DR. No matter what the router ID is set to, no matter what the priority is set to, whichever router you configure first, that becomes the DR. So it's a little misleading to say let's go ahead and set the router ID to the highest value to make sure that router becomes the DR, because you can't guarantee that.
You have to bounce the DR before you get that to work, right?
Well, you'd have to bounce all the routers, because the DR and the BDR would have to go down in order for somebody else to take over as the DR, unless the other router was already the BDR. Does that make sense? If router 3 was the BDR and router 2 was the DR, I could reload the process in router D, or router 2, and that would force router 3 to become the DR. But then again, if router 3 fails again, you'd have to do that all over again.
Well, if you replaced it, you want to put it back as DR.
Right.
You have to bounce those two.
But again, there's no guarantee it's going to stay that way. I mean, it's likely to stay that way, but there's no guarantee. So, and OSPF doesn't self-correct. Right?
Is there any way of manually setting it down?
No, there's no way to force a router to become the DR. The only way is to make the other routers ineligible. But then you run the risk of losing all your adjacencies because there's nobody else that can become the DR if your DR fails. I guess the bottom line is it's not really that important anymore.
Crapshoot.
And it is a crapshoot. You know what the dead timer is? That's how long I'm going to wait before I delete the neighbor. What about address? That's the physical address of my neighbor. That's like the next hop address. And this is the exit interface. So we see those two pieces are common to EIGRP. This is the stuff that goes into my routing table. Right? That's the stuff that goes into my routing table for the routes that I learned from that neighbor. Exit interface, next hop ID. All right, so we did this configuration. Are there any questions about the commands that you entered on these routers? Do you guys understand generally the syntax? All right. So everybody go into router number 3. Run this command. What command? What command is this?
Process 1.
Show IP protocols. That's right. Show IP protocols. For some reason it's not listed here. I don't know why, but show IP protocols is the command. So go into router 3, run to show IP protocols. Again, the router ID shows up. All right. Maximum paths 4, we know what that means. Maximum number of load balanced paths. Here's my network statements. Why 240.0, 240.4, and 240.8? Because those are all my /30s, all my serial links. Now, you could have done this more efficiently by doing just 10.10, 240.0 with a 255 at the end. And there's nothing wrong with doing it that way. Routing information sources, I always thought this was kind of funny. Yeah, it shows all my neighbors, but I show myself as a routing information source. I think that's kind of funny. But I guess I'm a source of routing information. All right. Okay. So we use show IP protocols for RIP. We use show IP protocols for EIGRP. We use show IP protocols for OSPF. And I think you guys, by this point, should be getting a pretty good idea of what these outputs represent. If you see one of these outputs on the test, you should be able to figure out what you're looking at based on these outputs. You should know that this is how I entered my network statements. You should know that these are my neighbors. You know what 110 means. You know what maximum paths means. Okay.
Distance, default distance, it'll be the same in every OSPF protocol.
Yes, because OSPF's administrative distance is 110. I think the other day I might have said EIGRP was 110. I don't know why I would have said that, but EIGRP is 100. Neighbors. Now, this topology is actually pretty good because guess what? There's one router in the center of my network that should be a neighbor with everybody. So if you can go into router 3 and you see all those neighbors, well, the only way you're going to do that is if you fix the problem. Did anybody find out what the problem was? What was it?
Encapsulation.
There was an encapsulation mismatch on the serial link. One side of the serial link is running PPP, the other side is running HDLC. They have to match. So either configure PPP on both sides or remove PPP from one side. Giovanni got the fact that the layer 2 was down. Probably saw that from a show IP interface brief. If you do a show run and compare the configs side by side, you can also tell one has PPP and one doesn't. How do I remove PPP from the interface? No encapsulation PPP. Because what is the default encapsulation for serial links? It's HDLC. If you want to add PPP on both sides, just encapsulation PPP on both sides.
You didn't have authentication on both sides either, did that matter? Not for the link.
You don't need authentication. If you are running authentication, it has to be on both sides, but I wasn't even running authentication anyway. I was just running regular PPP.
Or we have chat authentication in there.
Yeah, the one with PPP had authentication.
Oh, it did have authentication, okay.
On one of the serial links, but not the one that was broken.
Okay. Yeah, so your best bet is just to remove PPP. Because you don't want to have to configure authentication. We're not even going to talk about that until tomorrow. All right? Why do we see dashes for the state? Dash, 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 and priority of 0. Why do we see that? Because those are serial links. We don't do elections on serial links. That's why you see the dashes. There's no election on a serial link. Router 5, router 6, router 4, those are all on serial links. Okay?
So then, that made each one of those 3 routers of a DR. If there's no election between them. Or it just means
All 3 of these routers are DRs, yes.
Okay.
But they're DRs for their Ethernet networks.
I see.
Which is kind of pointless because there's no need to be a DR when there's no other router to talk to. But OSPF doesn't determine that. OSPF doesn't say, well, there are no routers, so I don't want to be a DR. If it's a multi-access network, the election occurs, period. You won't ever see it because there's no adjacency on those links.
So in order for them to all to get together, you'd have to have an Ethernet link between them?
What do you mean, in order for them to all get together?
Like for failover and for just redundancy, you could have Ethernet links between them for.
Yeah, you could have connections here, or you could have connections back to here. That's not.
Then there wouldn't be a.
This is a hub and spoke design, so these are like branch routers. This is my corporate office. It's what we call a hub and spoke design. Okay. This command does not work in Packet Tracer, but it's a very useful command in the real world. Show IP OSPF interface brief. The nice thing about this is it just lists all the interfaces on your router that are running OSPF. Tells you what the cost of the interfaces are, how many neighbors exist on that interface, if they're full adjacencies or if they're partial adjacencies, what the address and mask on the interface is, what area it's in, what part of process ID, OSPF process ID it's running in. Very useful command for some basic troubleshooting of OSPF. Unfortunately, it doesn't work in Packet Tracer, but there you go. What about passive interface? We do have some interfaces in our topology that we would want to make passive, don't we? Which interfaces would we want to make passive in this topology? All these guys, right? These guys and these guys. Because there's nobody out there to hear OSPF. Of course, we already know how passive interface works because it's the same as it is with EIGRP. We use the passive interface command. Okay? What about routes? Now, the routes in OSPF are a little bit easier to configure or to understand. Take a look at router 3. If we do a show IP route OSPF, I can see that we actually have 1, 2, 3, 4, 5 routes. That makes sense in router 3 because there's 1, there's 2, there's 3, there's 4, there's 5. Those are the 5 routes I'm seeing. To get to the 110 network from router number 3, which is this one over here, it has a metric of 2. Now that looks like hop count, doesn't it? But actually it's not hop count. It's the cost of this link plus the cost of that link. This interface and this interface. And we already determined that the cost of a gig interface is 1. So 1 plus 1 is 2. The metric for OSPF is a lot simpler to visualize than it is for EIGRP. Why is the cost of the path to 112 65? Which interfaces are included from router 3 to get to the 112 subnet? This interface and this interface. I noticed that if there's a mismatch, it doesn't pick the command 10.10.240.0. You mean if you mistype a network statement? Not sure what you mean by that. Oh. Well, one doesn't have anything to do with the other. This is layer 2. Network statements are layer 3. So it doesn't matter what your network statements are. If you don't fix the layer 2 problem, the layer 3 thing doesn't matter. They're completely separate configurations. One is not related to the other.
You still put the network statements in.
Sorry?
You can still put the network statements in.
You can still put the network statements in. They're just not going to do anything because until you fix your layer 2 problem, layer 3 is not going to work. I'm trying to still understand what you're saying, though. If there is a mismatch, it doesn't pick the command network.
He said.
What he said, okay. Yeah, you can still put your network statements in, they're just not going to do anything. This is a layered approach, right? Physical layer has to work, data link layer has to work, network layer has to work. You can't jump right to the network layer if the first two things aren't working. All right? Again, I was asking why 65? Because we have this interface here, which is a T1. If you take 10 to the power of 8, 10 to the power of 8 divided by 1544000, because it's in bits per second, you get 64.76. You drop the remainder, that's 64. So the metric for this link is 64. We already know that the metric for a gig is 1. Add them together, that is your path metric of 65. So like I said, the metric for OSPF is much, much simpler.
The change with bandwidth on serial links, I mean, if you end up with like an T3 instead of a serial link, would that matter?
Serial is serial. T1 is T1. Because you can run frame relay where you actually have a CIR of much less than 0.544. That's where you would have to manipulate the bandwidth manually to correspond to the actual amount of bandwidth that you have. A high-speed serial interface is probably going to have a higher bandwidth though. All right? This is the same way of looking at a route. In this case, we're on router 1. Router 1 is right here. Going to the 112 network, metric of 66. Well, guess what? We got this link, which is a cost of 1. We already determined that these links are a cost of 64, and this link is a cost of 1. That equals 66. I love working with the metric in OSPF because it's so simple. Here's a visual representation of that. Bandwidth, bandwidth, bandwidth. Put those in the formula, add them together, that equals my overall path cost. How can I manipulate that? There's two ways, and this is on the test. If you change the bandwidth of an interface, of course that's going to affect the cost, isn't it? Just like we saw with the EIGRP, if we change the delay or change the bandwidth, it affects the metric. But there's another way to do it. You can also manually configure the cost. You can set the cost on the interface statically. If you set the cost statically, it overrides the use of any calculation. We generally don't like to do it this way, but it is an option, and it's on the test, so you need to know. All right? Now, here's another interesting thing. We're not going to actually do this as part of an exercise, but here's an interesting thing. Let's forget all this stuff down here. Forget all that stuff. That stuff doesn't exist down there. All right? I've got a connection to the internet on router 3. Now, obviously, default route, right? Default route points to the internet. You guys agree with that? Where's the default route on router 4 going to point to? Router 3. And router 2 to router 3, and router 6 to router 3, or whatever, router 5. You get the idea. All these routers are going to point to router 3 for the default, because all this default traffic flows towards the internet. Right? Got it? In OSPF, we have an option, because the problem I have is static default routes work great until I have redundant paths. Let's say branch 4 or branch 1, gosh dang it, branch 1 has a connection over to branch, or the headquarters. Branch 4, sorry. Router 4, yes, you got it. Router 4 has a connection to router 1. Now all of a sudden, I have two ways of getting to the internet. Well, the nice thing is, you put your default static route on router 3 pointing to the internet, and you execute this command on router 3. Default information originate. And what happens is router 3 starts to advertise to everybody else through OSPF, I am your default router. So router 3 is going to advertise, let me put this link back. Router 3 is going to advertise to router 4, I'm your default router. It's also going to advertise to router 1, I'm your default router. Router 1 is then going to advertise to router 4 that it has a default route as well, going through router 3. So if this serial link goes down, router 4 simply sends its default traffic this way. It's a way for us to inject the default route into the system through OSPF. It works very well. I don't have to statically configure default routes on any of the branch routers because they're going to learn them through an OSPF advertisement. It's good stuff. It shows up as an OE2 route. You'll learn about that in the CCNP class. OE2 stands for External Type 2. All right, but you can see that's a default route.
Star still means default.
Star means default candidate, yeah. All right. If you want to see the hello and dead intervals on an interface, you run show IP OSPF interface. This does work in Packet Tracer, and you can see your hello packets and your dead, or your hello timer and your dead timer. What did I tell you about the hello and dead timer in OSPF? What did I tell you about the hello and dead timer in OSPF? Between neighbors, they have to match. I also told you that the dead timer was 4 times the hello timer. But the other thing I told you was that in order for two routers to form an adjacency, those timers have to match. If the timers don't match, the routers will not form an adjacency. Here's an example where I've gone in and I've adjusted the hello timer on the interface. The neighbor goes down. Neighbor goes down because the timers don't match. You can also set the dead timer as well. Each of these timers can be set individually. If you do see the OSPF lab on the test, one of the issues is that one router has a different timer value than the other router. It's very easy to see because it's right under the interface. If you don't see hello and dead timers specified on the interface, then it's using the default values. Check it out. I did a debug. I received a timer of 40. I'm configured with a timer of 100. I received a timer of 10. I'm configured with a timer of 50. So, oops. So those are not going to match. Those are not going to match. All right. Troubleshooting OSPF, pretty much the same thing. Make sure the interfaces are up and running. Are the interfaces, network statements, including the interfaces, do the areas match? Or do you have passive interface configured? Are all the areas connected to 0? We can't have areas that are not connected to area 0 if we have multi-area OSPF. All right. Is there a routing source with a lower AD? What do they mean by that? Is there a routing source with a lower AD? Yeah, administrative distance. If I'm looking for routes in the routing table and those routes don't show up, I need to see if there's another route with a lower administrative distance. If I'm running EIGRP or static routes, those are going to go into the table before OSPF routes will. Right? And if the traffic doesn't take the desired path, I need to analyze my routing table. I need to look at the cost of the interfaces. I need to look at the bandwidths to see if the metrics have been manipulated. If the metrics have been manipulated, then the routing process is going to be flawed. Same thing with IPv6. All right? So, that is the end of our advanced routing discussion.